welcome to the deep dive. Ever, ever stop to think how much complex math might be hiding right there, like in your kitchen pantry?
It's kind of surprising, isn't it?
Yeah. So today, we're actually cracking open that idea. We're looking at how concepts you might remember, maybe vaguely, from a calculus class.
Uh-huh. Differentiation, integration,
Yeah,
those guys?
exactly. How those are, well, fundamental tools in the world of food science. Which sounds maybe a bit technical, but stick with us.
Yeah, we've been digging into some sources that really lay out these connections pretty clearly. It shows this isn't just, abstract math. It's very much applied science.
Right. It affects the food we eat every single day. So our mission here is to unpack the main ways calculus gets used, try to understand why it's so essential.
And hopefully maybe make you see your next grocery run a little differently.
Okay, let's unpack this.
So what's really interesting, like right off the bat, is packaging.
Packaging, you mean like designing a box? Seems straightforward, length, width, height.
Well, yes and no. For a simple box, maybe. But what about liquids or powders or things with weird shapes?
No.
Or think about containers with curves like those fancy bottles or even pouches. Or getting the exact volume right in a bag of chips so they don't all get crushed.
Ah, right. That's not just simple geometry.
Exactly. That's where integration comes in. It's the tool you use to calculate the precise area under a curve or, the volume inside a complex shape.
So engineers are actually using integral calculus for this.
Absolutely. They use it to figure out the exact volume capacity, especially when things aren't just standard cubes or cylinders.
And that precision matters because...
Well, our sources really highlight this. It's not just about getting it right. Optimizing that volume means less wasted material.
Okay, less plastic, less cardboard.
Right. And it means accurate portion sizes, plus you can pack things more efficiently for shipping. That hits the bottom line cost-wise, and it's better for the environment too.
Wow. So it's using abstract math to, like, squeeze efficiency out of packaging and logistics?
Precisely. It makes integration a tool for real-world efficiency and sustainability, actually.
That's a much bigger impact than I would guessed. Okay, so that's integration for packaging volume. What about the other big area mentioned? Formulations and mass balance in production.
Right. So now we're moving from the container to, well, what actually goes inside it and how it gets made. Mass balance is absolutely core to food production.
Keeping track of everything, basically. What goes in must come out or be accounted for.
That's the basic idea, yeah. Inputs equal outputs plus anything that builds up or gets lost, tracking every single ingredient.
Sounds simple enough on the surface. So where does the calculus come in? I mean, counting is just arithmetic, isn't it?
It is, if everything is perfectly steady, but real food production, it's dynamic. Things are constantly changing.
How so?
Well, ingredients get mixed, they react, they're heated, cooled, concentrations shift over time, flow rates might not be constant. You're often dealing with systems that are not in a steady state.
Okay, I see. It's messier than just batch A in, batch A out.
Much messier. And this is where those formulations come in and why calculus becomes, well, indispensable. Differentiation lets us describe the rate of change.
Like how fast something is happening at a specific moment.
Exactly. How quickly is an ingredient being used up in a reaction? Or how fast is something mixing? And then integration lets us figure out the total amount.
The total quantity processed or accumulated over a certain time period.
You got it. So instead of just snapshots, calculus gives food scientists and engineers the tools to model and predict how things like mass and concentration behave through the entire dynamic process.
So they're using differential equations, integral equations.
Built into their mass balance formulations, it lets them model mixing times really accurately, understand reaction speeds, how ingredients disperse, predict yields.
And that level of precision is key for what? Consistency, safety.
All of the above. Consistent product quality, batch after batch. Food safety, because you can control the process parameters much more tightly, and minimizing waste because you're optimizing reactions and flows. It's way beyond simple counting. It's about understanding continuous change.
It's actually incredible. These math tools, integration for the container shape, differentiation, integration for the dynamic process inside, they're just quietly running in the background.
They really are fundamental. They give us the mathematical language needed to, understand and control all those complex changes happening when we make food.
So wrapping this up then, what does this mean for you listening right now?
Well, maybe the next time you grab a packaged food item, a drink, a snack, anything, just pause for a second.
Yeah.
Think about the complex calculations that likely went into it. Not just the recipe, but the container design, using integration, the process control, using calculus for mass balance.
That makes you wonder, doesn't it?
It really does. What other everyday objects around you are built on similar hidden layers of mathematical thinking?
Mm-hmm.
Something to ponder?